AIDE ML. That's the name of the machine learning engineering agent we're unpacking today. It's a research paper from Weco AI and an open source implementation you can run yourself. Over the next 25 minutes, how it turns writing code into a tree search, what the benchmarks actually show, how to install and configure it on an RTX 4090, and 5 real datasets I ran it against, including a bug I found that was silently corrupting its results. Machine learning engineering is mostly trial and error. Engineers spend the bulk of their time not conceptualizing innovative solutions, but babysitting loops, tweak a feature, retrain, check the metric, repeat. The AIDE paper opens with exactly this observation. The work is tedious, it is compute-intensive, and it is enormously repetitive. The classical answer was AutoML. Tools like Weco, TPOT, and H2O search over a predefined space of configurations, which model, which hyperparameters, which architecture. But that space has to be designed by a human expert first, and the search inside it is fairly brute force compared to what an expert would do. Crucially, AutoML cannot step outside its box. It cannot invent a new feature or restructure the pipeline, because those things were never in the search space. Large language models changed what is possible. If a model can write and revise real programs, then the search space does not have to be a grid of configurations. It can be the space of code itself. That is a much larger space, but the language model carries enormous domain knowledge, and that knowledge narrows the search toward promising solutions. This is the core bet of the paper. So how do you turn writing code into something a computer can optimize? This is where the paper makes its most important move. Most general-purpose agents, like React, frame the task as a partially observable Markov decision process. The agent keeps appending observations to its context and treats the whole interaction history as state. That is flexible, but it has no principled way to break the problem down, and the context window eventually fills up. AIDE takes a different route. It models the task as optimization, where each candidate solution is evaluated independently, and the objective is stateless. That single choice is what lets it compare solutions directly and keep prompts bounded. Formally, the goal is simple. Let S be a space of possible solutions, where each solution is a Python script. Let Ch be a stateless objective function that scores a script, for example, validation accuracy. We want to find star, the script in S that maximizes AIX. Because each candidate can be evaluated on its own, we can use standard optimization machinery. This is the whole conceptual foundation of AIDE. It is worth pausing on the word stateless, because the objective depends only on the script in front of it, and not on the path taken to reach it. Every code revision stands entirely on its own. You do not have to unroll a single long-horizon decision process. You can just evaluate and compare. That is what makes tree search applicable, and it is what decouples prompt size from how long the run has been going. With the problem framed as optimization, the algorithm itself is remarkably compact. Here is the entire loop. Start with an empty solution tree and an empty base solution. Then repeat. Propose a new solution using the coding operator f, which sees the current solution and a summary of the tree. Evaluate it with h to get a score. Record the node and its score in the tree. Then select the next base node using the search policy pi. After n steps, return the best solution found. Propose, evaluate, record, select. That is AIDE. 4 components do all the work. The solution tree stores every script tried and how they relate to each other. The evaluator scores a script. The search policy picks which node to build on next, and the coding operator proposes the next script. This is figure 1 from the paper. Each circle is a complete Python script. Arrows are proposals from the coding operator. Notice some branches die in bugs, shown dark, while one path reaches the optimal solution, shown in pink. The coding operator has exactly 3 entry points, and each has its own prompt. Draft writes a completely new solution from scratch, deliberately simple, with no ensembling and no hyperparameter tuning. Debug takes a broken script and its traceback and repairs it. Improve takes a working solution and proposes exactly one atomic change, so that the effect of that change is directly measurable. That word atomic is doing real work. It makes every edge in the tree an interpretable experiment. The search policy is a hard-coded heuristic, not something learned. If we have not reached the desired number of initial drafts, draft a new one. Otherwise, with some probability, if a buggy node remains within the debug depth limit, debug it. Otherwise, improve the best working solution we have. So the policy encodes 2 practical rules. First, explore a diverse set of starting points, then greedily improve the best one, and never sink unlimited effort into a broken branch. There is one more piece, and it is easy to overlook. The summarization operator, sigma of t. Rather than appending every historical log to the prompt, it selectively extracts what matters: performance metrics, hyperparameter settings, and relevant hints for debugging. This is how AIDE keeps the stateless perspective while still benefiting from incremental reasoning. It gets the value of memory without the exploding prompt. AIDE also inserts a small static data preview into each coding prompt. Things like the number of rows, the column names, and how the data is split. It is deliberately lightweight. It is not a full exploratory data analysis pipeline. But it is enough to guide key decisions, like choosing a validation split or scaling a feature, without stuffing the entire dataset into the prompt. A clean idea is one thing. The paper backs it with evaluations on real Kaggle competitions, plus 2 independent third-party benchmarks. The protocol matters, so let us be precise. Before running, the competition's training data is split into an agent train set and a holdout test set. During code generation, the agent is given the holdout test inputs, but not the labels, and it must produce a submission.csv file, exactly like a human competitor. Performance is then reported as exceeds % of humans, the percentage of human Kaggle competitors that AIDE beats on the leaderboard. Here is Table 1 from the paper, on 16 tabular Kaggle tasks. AIDE, using GPT-2 or Turbo, exceeds 51.44% of human Kagglers on average. Compare that to H2O AutoML at 35.3% and AutoGPT at 32.3%. Notably, it also beats a human engineer working with ChatGPT at 41.2%. And AIDE lands above the human median in half of the competitions. But the average hides real variance. Figure 2 shows AIDE's performance across the full Weco Kaggle benchmark, sorted by score. On some tasks, it is near top tier, beating the vast majority of human participants. On others, it exceeds only a small fraction. Across the whole set, the average is 48.2%, and it outperforms the human median in 49.2% of competitions. AIDE is highly competitive in certain domains, and clearly weaker in others. This is the result that got the most attention. OpenAI built MLE-Bench, an offline evaluation over 75 real Kaggle competitions, and they evaluated several agent frameworks. AIDE paired with O1 Preview earned a medal in 16.9% of competitions. The nearest competitor, OpenHands, managed 4%. That is nearly 4 times as many medals. The paper notes that other frameworks tended to terminate early or struggle with iterative refinement, while AIDE's optimization-centric approach kept scaling with more trial and error. This chart is the cleanest evidence in the paper. It is the same underlying model, O1 Preview, with AIDE wrapped around it. Valid submissions rise from 62.6 to 92.4%. Solutions above the human median jump from 13.6 to 59.1%. The gold medal rate more than triples. And the overall medal rate goes from 7.6 to 36.4%, nearly a five-fold increase. All of these are statistically significant. The scaffold, not just the model, is doing the work. METR, an independent evaluation organization, took AIDE far outside its comfort zone. Frontier AI research and development tasks judged against top human scientists from DeepMind, OpenAI, Anthropic, and leading universities. Look carefully at this chart. In the first 6 hours, AIDE is ahead because it can iterate far faster than a human. But then it flattens, and the humans overtake it around hour 8. The paper is candid about why AIDE adopts a simple greedy policy that can get stuck in local optima. It is worth being clear about both sides. AIDE shines when there is a robust evaluation signal, when iteration is fast, and when a solution fits in a single self-contained file. On optimizing a Triton kernel, it actually surpassed every human expert. But it struggles on environments with larger codebases, or where a single improvement requires multiple steps of interaction. In one task, the paper notes, it was prone to repeating local patches instead of discovering new strategies. Let us get it running. Everything from here is from an actual install on Ubuntu 22.04 with an RTX 4090. Here is the target machine, Ubuntu 22.04, an RTX 4090 with 24 GB, NVIDIA driver 580 and QDA 12.9 already installed. We use Python 3.10 because that is what the repository targets in both its makefile and its setup file. 28 CPU cores, and remember that number because it causes a genuinely surprising problem later, and you will need an LLM API key or a local OpenAI-compatible server. Step 1. The environment. We pin Python 3.10 for ton and of locally with ASDF, then create a virtual environment using that exact interpreter. Never the system Python, and never conda. We also export the Hugging Face catch variables up front, so that any model a generated script decides to download lands on the data drive instead of filling up the system disk. Step 2. Installation, and the order genuinely matters. Install QDA Torch first from the Q128 index, then install the repo itself, which pulls in requirements.txt. Here is the trap. That requirements file lists bare torch, torch vision, and torch text for the agent's own use, and torch text pins an older torch. It can silently replace your QDO build with a CPU 1, so always verify afterwards. It must print true and name your 4090. And here is that verification actually passing on the machine. Torch 2.11 with QD 12.8 survived the requirements install. QDA is available, and the device is correctly identified as the RTX 4090. Make this a habit. Re-verify after any subsequent install, because a single unpinned dependency can quietly swap your QDA wheels for CPU ones. An honest note about the GPU. For tabular tasks, AIDE barely touches it. The language model is a cloud API call, and scikit-learn and lightgbBM run on the CPU in a couple of seconds. During a full run, NVIDIA SME shows about 600 megabytes used and 0 compute processes. The 4090 sits idle. If you want the GPU actually working, run the language model locally with Ollama. A 30 billion parameter coder model fits comfortably in 24 gigabytes, and AI supports it out of the box. Next, configuration. There are a few knobs that matter far more than they look. This is the shipped config. Notice there are 2 separate models. One that writes code, and a different one that judges the output. The search block holds the policy parameters we saw earlier, 5 drafts before improving, a 50% chance of debugging, and a debug depth cap of 3. And at the bottom, exec.timeout, set to 3600 seconds. That line is far more interesting than it looks. Here is the subtlety. Exec.timeout is not just a guard that kills runaway code. It is interpolated directly into the prompt sent to the language model. The impl guideline literally says, "Be aware of the running time of the code. It should complete within," and then the humanized timeout. So at the default of 3C600 seconds, you are telling the model it has a full hour to work with, and it will believe you. It will happily write a 500 tree gradient boosting fit. Lower it to 600 seconds, the prompt says 10 minutes, and the model writes cheaper code. This one number shapes what gets written, not just what gets killed. Overriding is done with key equals value arguments in the Hydra and Omecon style, not with dashed flags. 2 practical warnings from a real install. First, the ship default models may simply not be available on your API key, in which case every call returns a 4 or 3. Second, and this catches people, the GPT-5 family rejects any temperature other than the default. You must pass temp equals null, which the config layer then strips out of the request. The upstream project added support for exactly this. One more gotcha worth knowing. There are 3 ways to run AIDE and they behave differently. The command line accepts overrides. The Python experiment class silently ignores them because it loads the config with CLI arguments disabled. And the Streamlit web interface has no model selector at all. It reads config.yaml directly, so it fails outright if the default model is unavailable. The practical rule is that editing config.yaml is the only change that fixes all 3 at once. Now let us actually run it and see what comes out. 3 ways to run. The command line is the primary entry point. Point it at a data directory, describe the goal in plain English, and describe how to evaluate it. There is no YAML grid and no bespoke wrapper. The Python API mirrors it, returning the best solutions code and validation metric. And there is a Streamlit web interface on port 8501. This is the web interface after a completed run on the bundled house prices example. You paste your key, upload data, describe the goal and the metric, choose the number of steps, and press run. As the search proceeds, you get a live tree visualization and tabs for the best solution, the config, the raw journal, and a validation plot. It is the fastest way to get a feel for what the agent is doing. Every run writes 4 things, and it writes them after every single step, so even a killed run leaves inspectable artifacts. The journal contains the entire tree, every script, every plan, every metric, and the captured output. BestSolution.py is the winning script. And treeplot.html is this, the interactive viewer you are looking at. On the left are the 5 draft roots and the improvement chains descending from them, with the pink node marking the best solution. On the right is that node's plan and its full code. Theory is cheap. Let us point AIDE at 5 real datasets and grade it honestly. Here is the critical design choice. AIDE's own metric is self-reported by a language model reading the program's output, so we cannot just trust it. We follow the paper's protocol, split each dataset 80-20, give the agent the test in inputs but never the labels, require it to write a submission file, and then grade that file ourselves against the labels it never saw. That is the only way to know whether the agent is honest. Use case 1. The Titanic. This is binary classification. Given a passenger's class, sex, age, fare, care, cabin, and name, predict whether they survived. About 1,000 training rows and 262 held back. The metric is plain accuracy. AIDE scored 8.836 on the holdout, right at the well-known ceiling for this dataset, with only 2 of 10 nodes failing. This is the actual winning script, and the feature engineering is genuinely good. It extracts the title, Mrs. Miss, Master, from the passenger's name with a regular expression. Then it imputes missing ages using the median age of that title group, which is much smarter than a global median. It builds family size from siblings and parents, flags solo travelers, computes fare per person, and flags whether a cabin was recorded at all. Only then does it train an XGBoost classifier with stratified 5-fold cross-validation. Nobody told it to extract titles. It knew. Use case 2. Bike sharing. This is regression. Predict how many bicycles are rented in a given hour, from weather, season, and time features. Nearly 14,000 training rows. Because this is count data spanning several orders of magnitude, the metric is RMSLE, root mean squared logarithmic error, which penalizes relative rather than absolute error. AIDE reached 0.265, and this task showed the biggest gain from tree search of all 5. 2 ideas make this solution work, and AIDE found both. First, it log1+ transforms the target before training and inverts it afterwards, which matches the RMSLE metric it was asked to optimize. Second, and this is the elegant part, it encodes the hour and month cyclically, using sine and cosine. Without that, a model thinks hour 23 and hour 0 are 23 units apart, when they are actually adjacent. The sine-cosine pair puts them next to each other on a circle. Then like GBM with 5-fold cross-validation. Use case 3, California housing. Regression again, predicting the median house value for a census block from 8 numeric features like median income, house age, and location. A note on why this dataset. The classic choice here would be Boston housing, but scikit-learn removed it in version 1.2 because it contains a feature engineered on racial demographics. California housing is the same shape of problem, without that baggage. AIDE reached an RMSE of 0.437, about $43,000, with an R-squared around 0.85. Use case 4. Wine quality. This one is subtly different. The target is a sensory quality score from 3 to 9, an ordinal target, where being wrong by 1 is much better than being wrong by 3. So the metric is quadratic weighted kappa. What is interesting is that AIDE worked out on its own that it should treat this as a regression problem and round the prediction, rather than as plain classification. That is exactly the right call for kappa, and nobody told it. This run also had the lowest bug rate of all 5. Use case 5, the Ames house prices dataset, and the hardest of the group. AIDE features mixing numeric and categorical, from lot area to garage type to kitchen quality. The metric is RMSE on the logarithm of price, so relative error matters equally at every price point. AIDE scored 0.1154, which is a genuinely respectable Kaggle score. And remarkably, it got there despite 9 of its 10 nodes failing. Here are all 5 results together. 5 tasks, 10 steps each, about 50 minutes of wall clock and 39 cents of tokens. And here is the headline finding. Compare the AIDE val column, which the language model self-reported by reading the program's output, against the holdout column, which we computed ourselves on labels it never saw. They track within a few thousandths on most tasks. There is no systematic optimism. The agent is not overfitting its validation split, and it is not gaming its own judge. That is a real vindication of the paper's stateless evaluator design. And this is algorithm 1 made visible on the bike sharing task. Each red cross is a buggy node with no metric. Each green dot is a valid solution. The blue step line is the best score so far. Watch what happens. The 5 drafts plateau around 0.46, and then the improved steps drive it down to 0.27. That is a 1.7 times gain from tree search alone, on top of whatever the model would have produced in a single shot. This is not one lucky draft. The search is doing real work. Running this for real surfaced a genuine bug in AIDE, and it is a beautiful one. AIDE executes each generated script with Python's exec, passing an empty globals dictionary. But with no name key in that dictionary, Python falls back to built-ins, where dundername equals the string built-ins. So the standard if dundername equals dunder main guard is never true, and main never runs. The script exits cleanly. No output, no exception, in a third of a second. Then the evaluator, seeing empty output, invented a metric of 0.0. And because lower is better for RMSE, 0 beats every honest score. The greedy search locked onto a completely fictional optimum. 1 line fixes it, and bike sharing improved 3 times over. So what did we learn? On the left, what the paper claims, and we confirmed. The stateless evaluator is well calibrated. Tree search clearly beats one-shot generation. Draft diversity matters. And yes, the greedy policy plateaus exactly as the authors warned. On the right, things you only discover by actually running it. Exec.timeout silently shapes the prompt. One good draft is enough, even when 9 of 10 nodes fail. And most interestingly, on house prices, every light GBBM node hung on our 28-core machine and got marked buggy, so the search implicitly routed around a broken library, and the winning solution used random forest instead. Nobody told it to. Failure marking did it. So when should you reach for this? AIDE is a strong fit when you have a clear metric to optimize, when iteration is cheap and fast to evaluate, and when a good solution fits in a single self-contained script. For getting a solid tabular baseline in under an hour for 40 cents, it is genuinely impressive. It is a weaker fit when the work spans a large codebase, or when progress needs a strategic leap rather than a series of atomic improvements. Know which problem you have.
If you like this video, please subscribe and share. Thank you.